So welcome everybody. We've decided to get back to getting at our webinar series. Some of you have been on our webinars before. We were doing these really regularly for a while there. Got a bit busy around the shop and doing some renovations around the shop, and COVID going on kind of all slowed us down a bit, but we're going to get back at her now. So I think this is going to be an every 2 weeks thing that we'll be talking about one product or one opportunity or another. And we decided we wanted to lead it off. If any of you have noticed, we kind of rebranded a little bit from our Indulging with Insights logo to a Insights with Insight logo. So we want to start off talking a bit about the JP3 analyzers, and more specifically a little bit. And I apologize to some of our colleagues that are here from the US. We're going to focus a little bit on condensate measurements in Canada because there's some specific pipeline things that need to get done here. And we want to talk about how to optimize condensate production. Because that's really, as far of all the natural gas liquids or natural gas oriented products, whether it's pipeline quality sales gas, natural gas liquids like Y-grade, and condensate. Condensate's the big value one. And especially for some of the fields that we're developing up in Canada right now, up in the Montney, there's a lot of liquids production with that. So we want to talk about how to make the most out of that liquids production. So although we're going to talk about both about condensate production and near-infrared spectroscopy, we're going to start off talking a little bit more about the gas processing side of things and how to optimize a gas processing facility, and what sort of things we're going to look at, what kind of measurements we're going to talk about using to help do that optimization. First of all, a little bit about us, about Insight. We're a Calgary-based systems integrator and distributor. We're going to Northeast Calgary, have a large manufacturing facility available to us, 20,000 square feet of floor space, 9 bay doors, big overhead crane. We're fully AB 83 compliant. Again, for my American colleagues, we have some certain pressure vessel directives up here, and we're capable of doing all that kind of work. We've got a really strong documentation, drafting, design resources, a fairly big engineering team with lots of experience. All of our electricians are journeyman electricians. We fortunately recently had the addition of one of them on staff who's dual ticketing now for instrumentation as well. And we do full factory acceptance tests right here in Calgary. We run a full systems integration shop, from custom sample systems to process analyzer integration, PLCs and automation, full analyzer buildings. We'll do things right from the front end engineering design side of things. We've done a couple of feed project for people through detailed design into fabrication. Of course, we will do full commissioning out in the field, and we tend to focus hard on our service team. Biggest department in the company. We service everything that we sell. On the analyzers, sample systems is often a big concern and a big issue for people. And, we teach courses on how to properly design them to other people. So we're very strong on that sampling side of things. I'm going to start off talking a little bit about gas processing. And if we, in real simple terms, I always tell people everything's easy if you're not the guy who has to do it. But in real simple terms, a typical gas processing system is going to have some production gas, coming from whatever wells there are, an inlet separation system, often three-phase separation. And so when we talk about three-phase separation, we talk about, for those of you who are just joining us, don't worry, you only missed the boring parts a little bit about our company and none of the good parts about technology stuff, so it's all good. So we're talking a little just a bit about gas processing and kind of what goes on there, and then sort of we're going to talk about where spectroscopy and analyzers are going to fit into that later. So, we have some inlet gas, some produced gas from wellheads, typically comes in through some kind of three-phase separation, so we can separate off water, hydrocarbon liquids, and the gas phase side. Subsequently, assuming there's enough volume to make it worthwhile, there'll often be some additional processing to produce, what we often refer to as NGLs. In the US, you often hear it called Y-grade, and also to produce condensate. And so a C3 plus stream is what we typically refer to as natural gas liquids, and a C5 plus stream are condensate. And the whole separation side is, again, kind of easy if you're not the guy who has to does it. Gas rises to the top, waters go to the bottom, hydrocarbons go in the middle. Thing that makes it more complicated is that hydrocarbon liquids, I guess, should say, go in the middle. And the thing that makes it more complicated is adjusting the temperature and pressure. Those are what determines what hydrocarbons are going to be in the gas phase and what are going to be in the liquid phase. And so when we start looking at how to optimize a gas plant, a lot of it is going to come down to how do I figure out what the correct operating temperatures and pressures are in order for me to optimize the liquids production that I may be interested in doing. And so when we start thinking about that piece of it, we especially do start looking over at the condensate stabilizer side of it, because there's a lot of value towards the optimization. If we optimize the operation on the condensate stabilizer side of things, this again, we've got that inlet separator part, right? We're going to take that hydrocarbon liquids that's coming off of that inlet separator, knock out any water and feed that over to the water side, and then move it over to the stabilizer. And at the stabilizer, we're going to be trying to separate the parts that we want to keep as liquid and the parts that we want to go to further on into the plant to be treated on the gas processing side. And the trick to that, as we mentioned earlier, is to adjust the temperatures and pressures accordingly. The important thing to realize is how much value there is in adjusting those accordingly. If we can set the right operating conditions for the condensate stabilizer, first of all, we can make sure that the product that we're going to produce is going to meet specifications. And that's a big part of this whole thing. Talk a little bit about pipeline specifications and allowable butane contents, et cetera. But from other perspectives, when we can optimize that operation, we optimize our product volume. We produce more barrels of liquid. Again, most valuable product that's coming out of a gas processing facility. We also push less gas to the overhead side, which minimizes the amount of energy we need for recompression. So in current times, especially in Canada with our left-leaning government, there's a big thing about CO2 emissions and energy usage, right? And so when you can optimize your compression and minimize that energy usage, it also lowers greenhouse gas emissions. Most often when we optimize a stabilizer as well, means that we're going to put less heat into it. We're going to actually not reboil. We're certainly not going to overboil it. And so that can minimize our energy for reboiling, which again reduces emissions. But the most important part of it is we can maximize revenues by maximizing dollars. This is really where the big money is to be made. And if we don't do it properly and we produce off-spec product, there's penalties at the pipeline side, and that's where the big money is to be lost. So the value of doing the analytics properly in this application is that you can try to maximize your revenues and minimize penalties and minimize emissions all at once. It's really a win-win-win kind of thing. The thing we're trying to do is strike the right balance. We're allowed to have a certain amount of what's referred to as C4 minus in Canada, at least. This is and I apologize again to some of my US friends, this is a very Canadian-oriented view on condensate. C4 minus will also be referred to as deemed C4. And it's really how much light ends there is. It's the thing that causes high vapor pressure. In the US, vapor pressure is usually a bigger concern on the produced product than butane contents. Here it's the C4 minus, which is related to the butane, propane, ethane, and methane in the condensate. If we run our condensate stabilizer too cold or at too high a pressure, we end up with too much of that C4 minus in there, and we end up paying penalties. And the penalties are pretty substantial. For every percent too much C4 minus you get, it's 1% of the product they pay you $0 for. And so you just put a whole bunch of barrels in my pipeline, but you get paid $0 for those barrels. If you run it too hot, if you run the condensate stabilizer too hot or at too low a pressure, what happens is you boil more of those C4 minuses over to the gas phase side, but some of your C5 and 6 goes along with it. You're in this equilibrium situation where you're trying to keep as much of it in the liquid phase as possible, but not go off spec on this guy. So if we overboil it, we lose production volumes, you consume too much energy, and we put more into recompression. And so there's a bunch of issues here. And if everything else ran stable, it wouldn't be that hard to find your set points. You pull a few lab samples, you'd find out, well, this is my optimum temperature and pressure. The issue is that optimum temperature and pressure changes constantly. It changes with every change in the feed composition. It can even change with ambient temperature. You know, when we have a temperature measuring device in a big vessel like a stabilizer, if it's hot outside, there's different heat losses towards the wall and through the thermal well that the RTD is in. And so even things like ambient conditions changing can change what your set point as measured by those transmitters should be. So it becomes a difficult kind of issue. Couple into that not everybody has a really great grasp all the time on even how the specifications get applied by the pipeline company. So we found that when we're working with clients, we're sometimes in that position of trying to educate them a little bit about this is actually how your penalties get applied. And these are the criteria you're trying to hit. And this is how you're going to adjust process operations to get there. So Jess, I think we were going to do this as a poll, but I think I'm just going to talk through these points. So we're not going to put the poll up. Some of the questions that come up for us is, or for our customers is, first of all, understanding how condensate equalization gets done up here. So we have a thing in Canada called equalization. They want to say, not every barrel of condensate is equal to every other barrel of condensate. And so they have a certain formula they use. You get paid different amounts if you're at different densities and C4 contents. And it even changes quarterly somewhat. So right now, the reference density for condensate is 750 kilograms per cubic meter. It'd be like a specific gravity of 0.75 since water is around 1,000 kilograms per cubic meter. So this is the reference number that everything is compared to. That density affects condensate pricing. You get a credit or you get paid more for your condensate if you're under 750, and you get paid less if you're over. So trying to hit the right density on your condensate is really important. Slipping more butane into your condensate lowers the density. So slipping butane in actually helps you to get to this credit. Then they have this other thing that they calculate in the pipelines called the deemed C4. And the deemed C4 is calculated by taking 3 times the methane, ethane, and propane in the condensate and adding it to the butanes, NC4 and IC4. So to optimize, you really need to know how much of those 5 components are present in your condensate. And it's a more significant way, and it affects penalties in that you actually get paid you have to pay a penalty if you're over 5%, but you get no credit for being under. So the way the pipeline companies have set this up is it's a bit of a win for them, because if they can scare operators enough to run low on their C4 minus, to run at 3%, they get this product come into their pipeline that they don't have to pay any extra for, but it leaves them room to blend butane in. So if you're a plant operator, what you want to be doing is try to leave them as little room as possible so you can produce as much volume as possible. So the whole condensate, and if any of you are interested, you just have to Google condensate equalization, and you'll see where they give you all the formulas and the latest values. Right now, 1 meter cubed, which is around 6.5 barrels of on-spec condi, is around $511 Canadian. So if you can increase your production even by a couple of cubic meters a day, by 13 barrels a day, you suddenly get to print an extra $1,000. So this opportunity to optimize is a direct impact on the cash flow, because if your operating costs stay the same or actually get less because you're burning less energy, this is a direct impact on cash flow and profitability. So on that optimization side then, what we want to be able to do is adjust temperatures, perhaps recirculation rates, perhaps pressures, to optimize that production of condensate and stay on spec.
Some of it's confusing. Most of it.
This will usually minimize your amount of energy consumption because you're going to run lower reboiler temperatures and lower volume to compression. But that optimized stabilizer set point is going to change as inlet separation changes due to pressures, temperatures, and compositions. So to optimize this, we really require a measurement of composition. That point gets argued a little bit, and I'm going to address that argument on a subsequent slide. By the way,
I wonder if we should maybe remind people if they have questions or if they're confused about what's going on to feel free to interrupt at any time or type it into the chat, and we'll make sure we address it. Yeah,
the good point, Scotty. I was just about to say exactly the same thing. By the way, I'm used to getting interrupted by Scott. And, and so, yeah, if there's any questions, feel free.
When I go to today. So.
Pardon me? Oh, is that me? Maybe that wasn't us. Might have been a mic on. Okay, so optimizing stabilizers. It requires a measurement of composition. And we commonly think of gas chromatographs as compositional measurement device. So I'm going to highlight this. This is, our stance on this. If you want to do this properly, you really need to do a measurement of composition. Online chromatographs are used in a lot of applications, and often they work great, some applications. This is one where online chromatographs, especially on plant condensates, can be really difficult to get working. People think of, when we hear something like a word like, well, we're going to sell natural gas, or we're going to sell crude oil, or we're going to sell condensate. Well, that all condensates and all crude oils are going to be similar. Condensate differs from what field it are from the type of processing vessel. So this is a sample of a natural gas condensate off of a debutanizer tower. And as you can see, it's almost water clear. Doesn't look like there's very much dirt in it. Could probably imagine it'd be easy to run through an analyzer, and it is. It's one of the easier ones to measure on. Condensate straight out of a gas plant down here in southern Alberta. I don't know how easily it shows up there, but you can see there's a little layer of sludge right there at the bottom in it. And this is condensate out of one of the main Enbridge pipelines. Dark black, it's got particulate all through it. So the difficulties when we're trying to measure condensate isn't so much the analyzer itself, it's can we get a good sample to that analyzer? When we start to put in an online analyzer that samples from the bottom of a stabilizer tower, we have sand, we have clay, we have dirt. When we're up in the Montney shales in northern Canada here, they're very waxy condensates. So if there's any kind of a cool spot anywhere, they start to wax up. Now we take that and we try to put that into a chromatograph or the sample system for a chromatograph that has 1/8-inch tubing and tiny little injection valves. And what we have is a system that ends up plugging off all the time. If it's not going to plug off, we have to have very large filters in it that can handle all of this particulate matter. So we're changing filters all the time. Results in high sample maintenance costs, sample system maintenance cost, and high operating costs. And we're going to talk about the kind of numbers we're talking about for operating in a couple of slides. First, I want to talk a bit about kind of what are we really doing in the optimization? So when we have a condensate stabilizer, depending on whose pipeline it's going to go through, there's going to be various specifications and requirements. The job here is to boil off the light ends, the part that the end user or the pipeline company doesn't want, and try to keep the heavier stuff that they do want in the liquid side. So, raw condensate or field condensate will come into the tower as a liquid. It's recirculated and heated. There's a distillation process going on here. So the light vapor ends go to the overhead, and the saleable liquid, this is the stuff that we're going to try to push out to the pipeline for dollars, comes out of the bottom end of the stabilizer. The question is have we optimized the dollars and does it meet all the specs? And it's important to know that if we were to overboil the condensate, suppose we're coming in with a total of 106, this is a simplified case, by the way, but suppose we're coming in with a total of 106 barrels of liquid. 98 barrels of it is C5 plus, it's the stuff that for sure we can sell at condensate, and 8 barrels of it is stuff that is the butane. We're allowed to have some, but not too much. If we overboil, if we cook this condensate too much, what happens is we push more of the butane up onto this side. So the example we've used here is they've boiled it down to the point where they're only at 2% butane. So then they would have approximately their 98 barrels of C5 plus, 2 barrels of butane, a total of 100 barrels. Did this slide when prices were really low, so at $20 a barrel. Right now, it's more like $70 a barrel. So let's just make a little change here, $70. That 100 barrels is now worth $7,000. So that's all well and great. But now what would happen if I actually made a measurement there and said, oh, I've got room. I'm allowed to have 5% butane. I'm allowed to slip more butane to the bottom. So I'm going to lower the amount of heat that's going into here and see if I can optimize that number. So if I put an analyzer in there to give me some control on that bottom end, on how I'm controlling that stabilizer, again, we'll do it with the new pricing. Now I can get that up to 103 barrels, 3% more product. So great, I have to do the math in my head now. 103 times 70 is now $7,210. I was $7,000 before. I just got this extra $210 by lowering the amount of heat, lowering the energy consumption of my condensate stabilizer and optimizing. So our point here is that by controlling the process better, we can both use less energy and produce more product and make more money. So the value that comes in, again, is that in the custody transfer specifications, we're required to be less, or we pay a penalty if we're more than 750 kilograms per cubic meter. And we pay a huge penalty. Every barrel that's produced that's more than 5% C4 minus, we get paid $0. So our goal as a plant operator is run as close to that 5% as possible, but not over. And the value proposition of putting an analyzer in then is it allows you to do that. And again, I put some numbers together with kind of more current day values and typical numbers we'd see up here. We have a client right now who produces about 400 cubic meters a day of condi. If he increases, he optimizes on his C4 and he adds 6 cubic meters a day. A cubic meter right now in Canada is worth about $511. It's an extra $3,000 a day, around $1 million a year in additional revenues, from which he's also seeing energy savings, compression savings, and not getting into that penalty position. So the value proposition, this is the value of measurement. The value of measurement is, in this case, is that putting an analyzer in and running closer to that spec, running closer to 4.7, 4.8%, staying below the penalties point and running near optimized is going to allow people to pay off an analyzer installation often in several months. There are people out there that say, "Oh, you don't have to do the measurement. There's enough process data already. You know, you've got pressure transmitters and flow transmitters and densitometers, and we can do some data fusion kind of thing and build you a model which is going to tell you what the operating set point should be." And all of that works as long as you're doing labs every day constantly, because as soon as feeds or ambient temperatures or plant load changes, those models tend to fall apart. Requires far more lab data and consistent modeling and yearly subscriptions to software development rather than just putting in what you really need, which is measure the composition. And we've proven this works across multiple facilities. Again, people will talk about putting GCs in. Well, we do it with a gas chromatograph. Do you? How's it working? Small tubing, lots of parts, tiny injection valves, not compatible with a bunch of things in the condi, lots of consumables, frequent filter changes, carrier gas bottles that need to be changed out, injection gas valve rebuilds. So when we go and talk to our customers who've tried to do this, these are the sorts of things we hear. I just picked 3 client examples. Gas plant in central Alberta. They had 3-year-old gas chromatographs. So the analyzers were relatively new. They get a new operations manager in. He talks to his service guys and he says, "What's your biggest problem out here?" The maintenance says, "Analyzers are on our condensate are our biggest issue. We spend most of our service time just trying to keep those up and running." They took out their relatively new GCs, replaced it with JP3 and NIR analyzers. It's been operational and robust for 3 years now. In fact, we have a meeting scheduled to go out and see them where they're saying, "Hey, we're worried about what more, we know we haven't anything break down, but we're worried about what more spare parts. Should we have spare fibers? Because we want to keep these up and running all the time." They do almost no maintenance. Instead of it being a constant maintenance headache, they virtually never touch it. A major midstream producer, almost every drop of condensate that moves through Canada touches these people's pipelines. They had a full gas chromatograph online vapor pressure analyzer. Extremely well done systems integration, big custom shelter, redundant filtration, all kinds of things to keep it up and running. They'd had it running for years and they came to us and said, "We want to try this another analyzer on here because while what we're doing works, our maintenance costs and effort, we have one full-time person whose job it is to keep those analyzers up and running. And we go through over $50,000 a year in spare parts and carrier for the GC. Put an analyzer in them about 5 years ago, again, 5 years in service. Very low maintenance. They've now put it on every one of their condensate lines. A gas plant in the Montney. They had new GCs, relatively new. They had bought them about 3 years ago when we started talking about them. For 2 years, they've been trying to get them up and running on their condi. They had gone to the local distributor. They had gone to the US Sales and Service Office. They had spent over $200,000 in factory service on these analyzers that they had bought and still not up and running. We replaced them with this technology in January of this year. Within 3 months, they're full up operational and they're optimizing their stabilizers. So remember, if we're talking about a stabilizer that they can increase by 6 cubic meters a day, it's $90,000 a month. In 3 months, it's potentially paid back $250,000 already. So what is the solution I'm talking about with this JP3 things? We apply near-infrared spectroscopy to doing these measurements. Instead of using chromatography or some other technique, we shoot a beam of light across the sample. Insight's the local distributor. JP3 is the original equipment manufacturer out of Austin, Texas. The big advantages are no moving parts. Everything runs through half-inch tubing and piping. It doesn't plug off very easily like the eighth-inch stuff does. Fully capable of monitoring multiple streams in a facility. Very fast analysis, near real time. It can get down to be as low as about 15 seconds for a data update. Virtually no maintenance. I mean, having no moving parts and large diameter tubing eliminates a lot of the maintenance issues. Cell modem and cloud enabled, we can do full support of the analyzer's operating health and conditions via the cloud. And we run field support out of Grand Prairie, out of Edmonton, and out of Calgary. So why do we use near-infrared spectroscopy? Why that for hydrocarbon analysis? If you look at crudes or condis that are dark and black like this, you can say, well, there's no possible way you're going to use light to measure anything in this sample because they're very opaque. What this chart is showing is that these materials absorb a lot of visible light. That's why they're dark. But as we move beyond the visible, beyond the red, and into the infrared, they stop absorbing so much light. And you can get a beam of light to shine right through it in the near infrared until you hit certain wavelengths. At certain wavelengths, they start to absorb again. Think of wavelengths as like different colors. Wavelength here, blue is 400, here is around 800. Well, we move out to about 1600, and suddenly the hydrocarbons absorb again. But they absorb in very characteristic patterns. And those patterns can be used to identify and quantify which hydrocarbons are there. So when we're using near-infrared spectroscopy, we look in this wavelength region of light where hydrocarbons absorb, and the pattern of their absorption lets us tell how much of them is there and what kind are they. So that helps us on the measurement side, but then we want something that's robust for that sample to flow through. So we take what we refer to as a flow cell, and we send our sample of hydrocarbons flowing through it. Whoops, push the window out of the way. My pen is like a 1/16 of an inch too big. There we go. So our liquid hydrocarbons flows between these cells, or between these windows. Inside this block of stainless, there are these synthetic sapphire cores. You can see it's clear glass, looks like clear glass, but it's made out of synthetic sapphire. Sapphire has the advantage that it's the second hardest naturally occurring mineral next to diamond. And so things like sand, clay, bitumen, asphaltenes aren't going to be able to attack the surface. It's very chemically inert. Saline solutions, H2S, are not going to attack the surfaces. So our entire flow path, everything that contacts fluid, is this block of stainless steel and these sapphire rods. we take a laser, a custom designed laser that can emit light in the wavelengths that those hydrocarbons are absorbed. We'll shoot it across the cell. This is where the light gets to interact with that hydrocarbon fluid. We pick up that light and send it back over to the analyzer. So out in the field, there's this flow cell. You know, in Canada, we put it inside of an insulated box. We'll talk about that in a minute, but it's a very simple system. We just flow hydrocarbons through it. We don't do any filtration. We don't do any of the things they try to do to prepare a sample for a chromatograph, because it's all those sampling systems, things that create a lot of the maintenance requirements. Instead, we put it out in the field. We find some source of differential pressure. You know, it may be from an orifice plate, valve, pump, or just going from the sample point to a storage tank. We don't want to put a pump in specifically for the analyzer. It's a maintenance item. So we find some process differential. This allows fluid to be driven up through the tubing and return back to the process. We run everything in 1/2-inch tubing, nice and big, not easy to plug. So once we have the flow cell sitting out near the vessel or the operating facility that we want to optimize, we can put the analyzer part, I refer to this as the brain, back over anywhere in the facility. Fluid does not leave the process other than to come out, go through the flow cell and return. Nothing comes over to the analyzer. So that means we can put this anywhere, an MCC building, a control room. We don't need any special housing for the analyzer. We just want to meet an ambient condition of the analyzer certified to be operated from -20 to +50 C. So ideally, we'd like a non-condensing environment that's kind of got some temperature control, at least here in Canada. In the US, it gets mounted outside. From the analyzer, we take a fiber optic out that shoots the beam of light through the flow cell and bring a fiber optic back to the analyzer. So we collect some light that's after it's been absorbed by the fluid stream that's flowing in the cell. We can use this, by the way, I'm talking a lot about liquids today. We can use this both for gas phase or liquid phase applications. The light gets back to the brain, gets measured on the spectrometer, and then sophisticated data analysis algorithms look at the pattern of light and convert it into being, look at the pattern that they saw and create actionable data from it. This is your chemical composition, C1 through C6, C1 through C9, C1 through C30. This is your vapor pressure, your API gravity, your viscosity. The interesting thing is we can do this with multiple sets of fiber. So this one might be over here and be looking at condensate. And we can have a second set of fibers that comes out, goes over to this flow cell and comes back. And this one might be monitoring, let's say, Y grade. There's versions of the analyzer for a single stream, 4 streams, or 8 streams. So we can monitor as many as 8 different sample points, 8 different measurement points, doing a completely different analysis on each one. The analyzer just cycles through. I'm going to make a measurement of condensate on fiber set number 1. I make a measurement of Y grade on fiber set number 2. I'm going to measure inlet natural gas composition on fiber number 3. And it just bounces through them all. Again, with this fast cycle analyzer, we can get through all of those measurement points as fast as a single typical analysis is done on a gas chromatograph. Installations become very simple. This is a crude oil blending skid in Saskatchewan. They have a sample of crude oil coming out, going into our panel, returning back into the building. Inside the panel This is where our infrared cell is. And then we have a few other devices. The yellow thing that's there is just measuring, is there actually flow? And temperature and pressure transmitters above the cell, just so we know that the product is at the temperatures and pressures we normally see. So this is an entire installation. The brain is mounted inside the building. You can see the fibers coming in from the bottom corner. And we're doing a real-time measurement of vapor pressure. It allows them to figure out how much butane they can blend into their crude oil. So again, blending butane into crude is another value printing, money-making type operation. And this gives them data to say, my product is on spec for the vapor pressure of my crude oil, but I've managed to slip some butane into there. It's like putting water in the whiskey in an old bar. I mean, it's a way to take a low value product and sell it as though it's a high value product. Put butane into the crude, still meet specification, and you sell $5 a barrel butane as though it's $70 a barrel crude oil. So what refineries do with gasoline all the time, butane blending and vapor pressure optimization for refineries is a big deal. I notice we have something going on in the chat, so I should probably check. Oh, what type of valve on the output back to the process? We're just typically using a ball valve, typically 40 series or 60 series ball valves on the way back. Gate valve often right over where gate valve right over where the probe is typically. And so, yeah, when you look in this panel, I mean, we put isolation valves on the inlet and the outlet side. Pressure and temperatures, there's a lab grab sample point in there. Why is it throttled? Good question. Greg, smart guy. Probably shouldn't be. I'm not sure why they didn't have that valve wide open when they took this picture. Because we do have a pump with a VFD drive on there. So they're controlling actually the flow to that thing with a little VFD drive pump. But this one might have been taken before they put that in there, and they might have found they were getting too much differential across their process pump. So there wasn't a needle valve there, so they might have throttled that guy. Now we typically put a needle valve. We use one of those globe-like needle valves, like the Swagelok NB series, as a return valve so that we can actually throttle flow. Because we can mount the analyzer head, the flow cell, wherever we want, we can put it really close to the process. This has advantages. It means we have very short transport lines and faster response times again, and we don't have long lines that are going to get plugged off. So here's a typical installation on a condensate stabilizer bottoms. They had a control valve down there, and so we took the differential pressure to drive sample from the control valve through the analyzer and return back onto the other side of the control valve. And so it makes for, again, a simple transport system, not much going on in it, easy to maintain. Installation of the condensate stabilizer. This is at the Pipestone processing facility up by Grand Prairie. Insulated cabinet mounted outside, puts us right close to the process. Inside that cabinet, you see things that are very similar to the other installation that we had. Explosion-proof heater in the bottom, flow switch, flow cell, pressure, temperature transmitter. In this case, there's also an automated isolation valve in there. The analyzer was put back just in an MCC building. So there are electrical panels and things like that in the building. They just found a spot on the wall, brought the fibers and electrical connections in at the top, full analyzer installation done with no additional analyzer buildings built. Big time when we're putting a new analyzer in, if someone's putting a new analyzer in, a big part of the cost is often the life support system for that analyzer. They build a whole building around this new analyzer. So in this case, we can use an existing building and existing infrastructure. Similarly, we had a client a large gas plant. They had a deethanizer, a debutanizer, condensate stabilizer, and a C3 plus stream that were going to storage. And they said, we have a small building. We'd like it all put inside there. So we were able to put the analyzer, a single analyzer in there. And you see 2 flow panels beside it. So 2 of those infrared cells. They already had sample lines bringing samples of this fluid over the building. So one of those is running their debutanizer, one of those is running their condensate stabilizer, and then right beside them is the other 2 panels for the deethanizer and the C3 plus stream. So 4 streams mounted on one small wall, on one wall of a small building, analyzer mounted beside them, and they're getting full real-time analysis of 4 liquid streams at their plant. So when we compare, I mean, there's certain things that GCs do well, but when we compare using near-infrared spectroscopy versus using things like a chromatograph or a physical properties analyzer, with the NIR, we can measure right at the process and measure at line pressures and temperatures. Other analyzers, we often have to transport the sample from the process to where the analyzer is and do a bunch of sample conditioning along the way. This can lead to phase issues, phase changes. Biggest problem we can have is we lose the butane to a bubble. And all of a sudden we measure it and we go, there's not much butane in your liquids. Butane was lost in bubbles. The NIR, we can run everything in half-inch tubing or pipe with no filters or regulators. Those are items that may plug. Most physical property analyzers were running on 1/8" and 1/16" tubing, redundant filtration. A lot of controls have to be put around it. A lot of opportunities for things to go wrong. We have faster response time with the NIR, and we can do multiple measurements. We can do vapor pressure, chemical composition, API gravity, all off of a single sample. Can mount the analyzer anywhere we want it to be, rather than dedicating a single analyzer to an analyzer building that is needed for that device. Now, on the downside, we take a little while to build up our model. We have to do an inferential measurement, so we got to get data. In theory, the physical property analyzers are direct measurements. They can be done directly. However, if you can't get the sample system to work, whole trick with any analyzer is getting a representative sample. We make sure we can get a representative sample by putting the analyzer as close to the process with no phase changes in between it. This slide's a little bit old, probably should be updated. There's probably more than 225 installations and 600 measurement points across North America now. But there's analyzers are present in every active drilling region and basin across North America. They're active on a lot of the major pipelines. We didn't talk about it here. We're going to do another one of these talks probably in a month and a half from now, and talk a little bit more about crude oil blending and about transmix, or measuring the difference between batches as things move down pipelines, because a lot of our pipelines are batched. And one of the strengths of the analyzer is it can measure different things. And so now we can tell, well, are you on spec for gasoline? Are you running condensate right now? Are you on spec for jet fuel? And so we can look at different products as they move down the pipeline. We've installed more than 30 of these in Canada now, and probably actually closer to 40, 45 measurement points. Just have 3 on the build right now in the shop. And so for any of you who are on Calgary, our shop's always open if you want to come by for a visit and see what it is that we do. Greg knows you come by, and I might even give you some beer to take home. So anything else, please contact. If you've got an application you're thinking of, we've got a lot of applications we've developed already, and we're more under development. We've used these all across the hydrocarbon processing industry, from natural gas liquids, crude oils, and refined fuels. We'll send you out a PDF copy of this presentation, and we'll probably get a video of it as well. And the last page of it will give sort of my contact info, and Scott Galenza. Scott's up here and works with us, and he handles a lot of our outside sales. So try to keep this down to an hour, and we're at 12:54. So if there are any questions, be happy to take them now.